Hi, my name's Sue, and we will be presenting on the topic of flight delay analysis and prediction. The goal of our project is to predict flight delays, and we aim to help airlines and airports with predictive insights, helping them to enhance operational efficiency and improve passenger experience. The problem we will be covering, which is for a particular airport, airline, month, and year, how many flights are expected to be delayed. Our data set covers flight data for the past 20 years and covers various airports in the US. It includes flight details such as year, month, airline carrier, and airport codes. It also includes flight delay metrics such as number of flights and the reason for delays such as carrier, weather, national aviation system, and security. There is also additional information on the total duration of delays, cancellation, and divergence. Now moving on to data cleansing and pre-processing. We found 509 rows without numerical data, out of about 350,000 records. A closer look showed that this happens when airlines have no trips during a specific period for a specific airport, so we removed those records. There are 238 rows where the number of delayed flight value is NAN. We found no delays in these cases, but other issues, such as canceled or diverted flights. So the rows are valid and were kept. We did not find any duplicate rows. This correlation matrix shows that metrics that have the highest correlation with a dependent variable include carrier delay and NAS delay. Here is a heat map of delays by carrier and month. As expected, there seem to be more delays in the summer and winter months, where there is more extreme weather and more travelers. This highlights those airlines with more delays. Here we see which airlines have the most observations and monthly trends for the different delay causes, which seem to follow a similar pattern.
For our baseline model, we chose random forest model. And before actually modeling, we used the grid search to find the optimal hyperparameters for the model. We explored the following hyperparameters, and then the best parameters were obtained as such. And for the random forest model, we had to set the settings as follows. For first, the maximum features, for each split, the model considers the maximum square root of the total number of features, which introduces the additional randomness and thus increase the diversity among the trees so that they're not too correlated. The out-of-bag score measures how well the model generalizes to unseen data. Each tree is trained on the bootstrap samples. Not all data points are included. These out-of-bag data points are used to measure the model performance. For training details, we split the data into 80% training and 20% testing sets, and the random forest models would fit on those training data sets. The training score came out to be 0.9995, which is very high, which indicates the model is able to predict the response variable 99.95 of the time on the training data set, which can be a sign of overfitting, as the complex model may pick up on not just the signal, but also noise. The out-of-bag score is 0.9964, which is also high, which means the model is able to generalize very well on the unseen dataset.
Now, let's talk about results. After combining and analyzing the information from the learning curve and all metrics calculated, we classified our results into error, generalization, and learning. The model generalizes well. This is supported by the mean cross-validation score that closely aligns with the test score, suggesting the model doesn't overfit at most. Also, the more or less constant gap between training and cross-validation error in the learning curve, which further supports this, and the OOB score being near the test score that reinforces the model's ability to generalize. As we can see, the learning curve seems to plateau around 75 or 100,000 training samples, indicating the model might reach its optimal capacity efficiently without requiring excessive data. Now, our conclusions. While the model performs well overall, the significant difference between train and test RMSE warrants further investigation. This could be due to factors like data imbalance, noise in the test data, or insufficient model complexity. Analyzing feature importance could reveal if certain features contribute to overfitting or noise in the model. Techniques like partial dependence plots could be used to understand how individual features influence the predictions. In summary, This random forest model shows promising performance with good accuracy, generalization, and potentially efficient learning. However, the higher test RMSE compared to trained RMSE and potential feature-related issues may need further investigation.
Hi, my name is James, and I'd like to highlight a couple ways that we can improve this project. First, as you know, we have a very high test R-squared value of 0.99. We'd like to understand if this is being artificially driven up by having too many predictors in our model. Second, we'd like to build a simpler predictive model that only uses predictors that one might actually have available to them when trying to predict the number of delayed flights, such as airport, month, and carrier as predictors. With that, I want to say thank you for listening to our presentation, and we hope you enjoyed it.